EvShutter, transforming events for unconstrained rolling shutter correction. Due to the sequential readout of rolling shutter sensors, images or videos can look distorted or wobbly. In this example, a rolling shutter sensor captures the blades of the fan elongated or shortened. EvShutter leverages an auxiliary event sensor with very high temporal resolution. The events can capture motion and brightness changes during the acquisition of the rolling shutter sensor, which we use to estimate a global shutter image. Our main contributions are a novel filter and flip event transformation, which eliminates the need for linearity assumptions of the motion. Furthermore, we present a novel rolling shutter and blur simulator to obtain highly realistic rolling shutter images with ground truth global shutter frames and capture a dataset with real events. Additionally, we adapt a state-of-the-art event-based deblur method by introducing optical flow, which improves performance and improves interpretability. The most frequently used methods for rolling shutter correction are IMU-based. Those methods estimate a camera rotation or pose to compensate rolling shutter artifacts due to global motion. However, they fail in the presence of local motion or large translations. More recent methods use multiple frames of a video to compute optical flow and approximate the motion during image acquisition based on the motion between frames. However, they only work well for relatively small and linear motions and are sensitive to image degradations. Event-based correction methods do not suffer from those issues and enable the correction of nonlinear motions. To obtain the first dataset with real events, rolling shutter frames, and global shutter ground truth, we built a beam splitter setup with global shutter camera and event cameras. We capture global shutter images at a frame rate of approximately 160 fps, which allows us to obtain high-quality images with relatively long exposure, while previous methods recorded multiple thousand fps, which negatively impacts image quality. The rolling shutter images are obtained using our novel simulator. Firstly, we adaptively upsample the video so that the maximum displacement between frames is at most 1 pixel using super slow-mo. The interpolated video stream can be thought of as a discrete approximation of latent frames. To simulate rolling shutter and blur, we set a continuous exposure time and rolling shutter readout delay, which defines the width and gradient of the depicted parallelogram, and by that the blur and amount of rolling shutter distortion. Because the frame rate of the adaptively interpolated video is variable, we compute the weighted average of the interpolated images for each row depending on the time span over which this latent frame was visible to the camera. As ground truth global shutter, we just use the matching original global shutter frame. As you can see here, our adaptive interpolation scheme eliminates temporal aliasing artifacts, which can occur for fixed interpolation factors, and simulate realistic rolling shutter and blur. To use events for rolling shutter correction, we introduce our filter and flip event transformation. In the top diagram, you can see the time on the horizontal axis and the image rows on the vertical axis. Rolling shutter images are not captured in a single moment, but each row is captured after the other, leading to this diagonal line for the rolling shutter image. To retrieve a global shutter image at the reference time, we firstly filter out all events which did not capture changes between the global shutter and the rolling shutter frame. In a second step, we flip the chunk of events before the reference time to ensure that the direction in which the events encode the changes are consistent. In this case, events encode the changes from global shutter to rolling shutter frame. However, this choice of direction is arbitrary. The flipping is performed by inverting polarities and mirroring events temporally around the reference time. By choosing different reference times, we can estimate different global shutter frames with the same rolling shutter frame. In our ablations, we show how the filter and flip transformation is beneficial for all parts of our model and improves the total performance of our method by 2.6 dB in PSNR. We outperform image-based methods and the previous event-based method EvUnroll on our challenging RS-ERGB dataset. Deep shutter unrolling was the best performing image-based method on our dataset, but often failed completely due to the large motion between frames. EvUnroll is able to correctly estimate the coarse shape of the object, but shows significant ghosting artifacts. We outperform image-based methods by more than 9 dB in PSNR and the event-based method by 0.75 dB, which can be visually noticeable, as you can see in the examples. We also evaluate on the public FastTech rolling shutter dataset, for which we synthesized events. Comparison to the image-based methods deep shutter and rolling and RSCD is shown here. We outperform the best image-based method by more than 4 dB in PSNR and EvUnroll by 1.1 dB in PSNR. In the presence of fast motion, we often also have to tackle blurry frames. For this, we adapted a global shutter event-based deblurring method. While the original method uses raw events to compute offsets and masks for deformable convolutions, we compute the optical flow during the exposure time of the image. Based on this flow, we then predict the offset and masks. As shown in the table, our method improves the deblurring performance in all metrics. Furthermore, as it can be seen on the right, our method improves the interpretability of the offsets and masks, which now follow the motion in the scene. We also compare our method to EvUnroll on their dataset with real events and real rolling shutter images. However, this dataset has no ground truth. We show that EvUnroll improves significantly when trained on our data with real events and simulated rolling shutter images. Our method, however, still gives visually improved results. Thank you for watching.